Fluids are everywhere, from the air we breathe to the water we drink, and even the oil flowing inside machines. But in fluid mechanics, not all fluids behave the same way. Some flow smoothly, some resist motion, and some are just plain weird. Today, let's break down the types of fluids in the simplest way possible, with examples you can actually relate to. Let's dive in. What is a fluid? Before we jump into types, let's first understand. What exactly is a fluid? A fluid is any substance that can flow and doesn't have a fixed shape. It takes the shape of its container. So yes, both liquids and gases are fluids. For example, water flows and takes the shape of a bottle. Air flows and fills any container. Easy, right? Now let's talk about the different types based on how they behave when force is applied. Types of fluids, based on viscosity and flow behavior. Ideal fluid. An ideal fluid is imaginary. It has no viscosity and cannot be compressed. It flows without any friction. In reality, this doesn't exist, but engineers use it for simplified calculations. Real fluid. Now comes the real world. Real fluids have viscosity, a property that resists motion. Every fluid around you, air, oil, water, is a real fluid. Example: honey flows slowly because it has high viscosity, while water flows faster because it has low viscosity. Newtonian fluid. These fluids obey Newton's law of viscosity, meaning the shear stress is directly proportional to the rate of shear strain or velocity gradient. Simply put, if you apply more force, it flows faster in a linear way. Examples: water, air, alcohol, and thin oils. They behave predictably, like your most disciplined student.
Non-Newtonian fluid. Here in non-Newtonian, shear stress is not proportional to shear strain. These are called non-Newtonian fluids because their viscosity changes with applied stress. Ideal plastic fluid. This one is interesting. It behaves like a solid until a certain stress is applied. After that, it flows like a fluid. Here in ideal plastic fluid, shear stress is more than the yield value and shear stress is proportional to the rate of shear strain.